In industrial robotics, the Jacobian matrix relates a robot's joint velocities to the velocity of the end effector, position, and orientation change. It is derived from the robot's kinematic equations. The Jacobian helps compute motion, control trajectories, detect singularities, and convert forces or velocities between joint space and Cartesian space. Here a video.
This video will explain the basic method of how to calculate the Jacobian for a simple robot. For an n-link robot with joint variables q1 to qn and following forward kinematics, we need to be able to find the Jacobian. So to do that, first step is write position equations. These are the equations that get the numbers in the position spot of the homogeneous transformation. So then we take the derivative of those equations to get velocity and put it in matrix form. X dot equals j theta dot, where x dot is end effector velocity and theta dot is joint speeds. So let's do an example of this. Here we'll do an example using the two-link robot and find the Jacobian of this. Step 1 is find the forward kinematics. Step 2 is take the derivative and get velocity. Step 3 is put it in matrix form. So we'll start with step 1, getting the x, y, z positions of the end effector. So x is going to be the x position of this, so we'll go all the way out here to the side, and then all the way up. To get to the end effector, we have to travel along the link. So first link 1, and then link 2. And it's cosine of theta 1 plus theta 2 because theta 2 is given with respect to link 1. So they add together to get the angle of link 2. So now we take the derivative of these and get velocity. Remember to use product rule because cosine of theta 1 plus theta 2 is going to have theta 1 inside of it and theta 2 inside of it. Next, we put these in matrix form. So we'll have the x dot matrix, which is really x dot, y dot, z dot. So that'll be a big thing. Then we multiply it by theta 1 dot, theta 2 dot. Now looking at this, we know that n is 2 because there are 2 joints. And m is 3 because this is a two-dimensional robot, so we could really move in x, y, and theta. We can't move in the z direction, so we're going to get rid of that, and we're going to make this become a 2x2 matrix. So here we can make the Jacobian be a 2x2 because this robot can't move in the z direction. So really what we care about is x and y. So to get matrix form from the velocity equations, we just need to put in the coefficients of those equations. Because if we recall, j equals del x, del theta 1 dot, del x, del theta 2 dot, del y, del theta 1. Actually, these aren't dots. And then del y, del theta 2. Okay, so the rows of Jacobian correspond to x and y. The columns correspond to theta 1 and theta 2. So we just need to put the coefficient for the x equation, x coefficient of theta 1 goes in the first spot. So that's minus L1 S1 minus L2 S2. That is what's times theta 1 dot. And then for the theta 2 dot, we just have minus L2 S12. And similarly for the y. So this is the Jacobian.